Is the universe infinite? Cosmic Enigma. Welcome to Cosmic Enigma, where we unravel the universe's deepest secrets. Does the universe truly stretch on forever, without end? Or is it a finite, boundless entity, like a colossal cosmic sphere? This profound question has captivated humanity for millennia. From ancient philosophers to audacious thinkers who challenged prevailing ideas at great personal cost. This enduring human curiosity about the universe's scale has driven our quest for knowledge. In the past, direct observations often led to perplexing paradoxes. Take Olber's paradox, for instance. If there were infinitely many stars, why is the night sky dark? This highlights a fundamental challenge. Our intuition about infinity often clashes with what we can actually observe. It also hints at a crucial distinction between the observable universe and the entire universe, a core theme we'll explore today. Modern cosmology, armed with powerful telescopes and complex theories, is now striving to unravel this age-old mystery, using observable evidence to paint a more complete picture of our existence. When scientists talk about the universe, they often mean the observable universe. This is a vast, spherical region from which light and other electromagnetic radiation have had enough time to reach Earth since the Big Bang. Think of it as a cosmic bubble with Earth at its center. But here's a mind-bender. Every location in the universe has its own observable universe, which might or might not overlap with ours. Our observable universe spans an astonishing 93 billion light-years in diameter. You might wonder, how can that be? If the universe is only 13.8 billion years old, the answer lies in the continuous expansion of space itself. Light from objects emitted 13.8 billion years ago has traveled to us, but those objects themselves have moved much further away due to this ongoing expansion. Our cosmic window isn't static. It's constantly expanding, revealing new, distant objects as their light finally arrives. The term observable refers to a fundamental physical limit set by the speed of light, not our technology. Some parts of the universe are simply too far for their light to have reached us yet. What's more, the accelerating expansion of the universe creates a future visibility limit. Light from objects beyond a certain distance may never reach Earth, meaning some galaxies could eventually vanish from our view as they're carried away faster than light can travel to us. This implies a fundamental barrier to our direct knowledge, even if the universe were finite but incredibly vast. To truly understand the universe, we must look into its distant past. Enter the cosmic microwave background, or CMB. This is the oldest light in the universe, a faint glow of microwave radiation filling all space. Think of it as the afterglow or relic radiation from the Big Bang, a cosmic fossil from the early universe. Its existence was predicted in the 1940s and accidentally discovered in 1965, providing crucial evidence for the Big Bang theory. In the universe's earliest moments, about 380,000 years after the Big Bang, the cosmos was a hot, dense, opaque plasma where light was constantly scattered. As the universe expanded and cooled to about 3,000 Kelvin, electrons combined with protons to form neutral atoms. This recombination epoch made the universe transparent, allowing photons to travel freely for the first time. These photons, stretched by billions of years of cosmic expansion, are what we now detect as the CMB at a frigid 2.7 Kelvin. The CMB isn't perfectly uniform. It has tiny temperature fluctuations, or anisotropies. These imperfections, mapped by missions like COBE, WMAP, and Planck, are incredibly important. They represent the seeds from which all the large-scale structures we see today, galaxies, clusters, superclusters, eventually formed. The structure of these CMB anisotropies, especially the first peak in its power spectrum, is a powerful tool for determining the overall curvature of the universe. The apparent size of these spots in the CMB acts like a cosmic lens, revealing the universe's geometry. So the CMB isn't just a baby picture of the universe, it's a direct measurement tool, providing precise information about the universe's initial conditions and composition, which in turn dictate its large-scale geometry and evolution. According to Einstein's theory of general relativity, the universe can take one of three overall shapes: flat, closed like a sphere, or open like a saddle. To visualize these, imagine a flat universe is like a perfectly flat sheet of paper. Parallel lines would remain parallel, and the angles of a triangle would add up to 180 degrees. A closed universe is like the surface of a sphere. Parallel lines would eventually converge, and the angles of a triangle would add up to more than 180 degrees. This universe would be finite in volume, but have no edges. You could theoretically travel forever without hitting a boundary. An open universe resembles a saddle. Parallel lines would diverge, and the angles of a triangle would add up to less than 180 degrees. The universe's shape is not merely a geometric curiosity, it dictates its ultimate fate. In a closed universe, gravity would essentially halt its expansion and cause it to collapse in a big crunch. An open universe would expand forever, with gravity only negligibly slowing the expansion. A flat universe would also expand forever, but at a continually decelerating rate, eventually asymptotically approaching zero. However, the presence of dark energy complicates this, leading to accelerating expansion even in a flat universe. This intricate interplay of geometry, matter, and energy density, and ultimate cosmic destiny, represents a powerful cause and effect relationship derived from general relativity. The current scientific consensus, strongly supported by CMB data, especially from the Planck mission, indicates that our universe is overwhelmingly flat. This means its density of matter and energy is very close to the critical density. While some initial Planck data hinted at positive curvature, more comprehensive data consistently points to flatness. A flat universe is consistent with, and in its simplest interpretation, implies an infinite universe. While a flat universe could theoretically be finite, e.g. if it had a toroidal or donut shape, current evidence and mainstream cosmological models do not suggest such a complex topology. The observed homogeneity and isotropy of the large-scale structure also support an infinite universe, as a finite universe would eventually show repetition. However, it is important to acknowledge that when one states the universe is flat, it refers to the observation that the small portion of the universe visible to us is consistent with being part of a flat surface. This is akin to standing in a fog on Earth. Our local observations might appear flat, even if the global shape is curved. This reinforces the limitation of the observable universe and explains why definitive proof of global infinitude is so challenging, even with strong evidence for local flatness. Now let's talk about cosmic inflation, a theory of incredibly rapid, exponential expansion that occurred in the universe's first tiny fractions of a second, immediately after the Big Bang. During this period, distances between points doubled every 10 to the negative 37 seconds, lasting at least 10 to the negative 35 seconds. Inflation theory, developed in the late 1970s and early 1980s, elegantly resolves several long-standing cosmological problems that the standard Big Bang model struggled with. One key issue is the flatness problem. Inflation stretches out any initial curvature of space to such an extreme degree that the universe appears incredibly flat on large scales, consistent with CMB observations. This is like inflating a balloon to an enormous size. Any small wrinkles on its surface become imperceptible. Another is the horizon problem. Inflation explains why the universe appears so uniform and isotropic, the same in all directions, across vast distances, even regions that were causally disconnected before inflation. These regions were once in thermal equilibrium before inflation stretched them far apart. Inflation also addresses the monopole problem. It predicts the dilution of exotic particles like magnetic monopoles, which should have been created in the early universe but have never been observed. This ability to explain diverse observations with a single mechanism makes inflation a highly compelling and widely accepted theory. Notably, tiny quantum fluctuations in the microscopic inflationary region were magnified to cosmic scales, becoming the seeds for the formation of all the galaxies and structures we see today. This indicates a profound connection between the quantum realm, microscopic, probabilistic, and the macroscopic universe, galaxies, clusters, implying that the very fabric of the cosmos has its roots in the inherent uncertainties of quantum mechanics. Many inflationary models naturally suggest an infinite universe. The process of inflation, once it begins, could continue indefinitely in regions beyond our observable horizon, creating a universe vastly larger than what we can ever hope to see. This leads to the concept of eternal inflation, where inflation never truly ends, resulting in the continuous creation of bubble universes within a larger, ever-expanding spatial environment. This is a speculative but intriguing idea of a multiverse, where our universe is just one of many. This concept, while speculative, is a natural prediction of some well-supported inflationary models and offers explanations for the fine-tuning of our universe for life. The universe is not static, it is continuously expanding, a discovery made by Edwin Hubble. This expansion is not galaxies moving through space, but rather the space between galaxies stretching. To illustrate this concept, several simple analogies can be used. Imagine raisins in a rising loaf of dough. As the dough expands, all raisins move farther apart from each other, and the more distant ones appear to move faster. Dots on a stretching rubber band will also move farther apart, with more distant dots appearing to recede faster. Galaxies are like dots on the surface of an inflating balloon. As the balloon inflates, the dots move away from each other, and the space between them stretches. This analogy also helps explain cosmological redshift, where the wavelength of light stretches as space expands, making distant objects appear redder. These analogies highlight the counterintuitive nature of cosmic expansion, where space itself is expanding, rather than objects moving within a static space. Observations indicate that the universe's expansion is not only ongoing but is accelerating. This acceleration is attributed to a mysterious force called dark energy, which makes up roughly 68% of the universe's total energy content. The dominance and mystery of dark energy underscore the limits of current scientific knowledge and introduce a major cosmic enigma directly related to the universe's ultimate fate and, by extension, its potential infinitude. This accelerating expansion creates a future visibility limit. Light from objects beyond a certain distance may never reach Earth, meaning some galaxies will eventually disappear from our view as they are carried away faster than light can travel to us. This implies that even if the universe is infinite, our observable window might not continue to grow indefinitely in terms of new observable galaxies. So, what's the verdict? The current scientific consensus suggests that the universe is likely flat, and a flat universe is most simply interpreted as being infinite. However, while the evidence is strong, direct proof of spatial infinitude remains elusive. One cannot see the edge of the universe because there may not be one, or because light has not had time to reach us from it. This highlights the distinction between a likely conclusion based on evidence and absolute proof, maintaining the enigmatic aspect of the universe. There is also a theoretical possibility that the universe could be finite but unbounded, meaning it is like a sphere or torus where one could travel forever without hitting a wall, and potentially see duplicate images of galaxies if light circumnavigated it. However, current observations, particularly the homogeneity of large-scale structure, do not support this possibility. If the universe is truly infinite, its implications are mind-bending. This could mean an infinite number of planets, stars, and even an infinite number of copies of Earth, each with slight variations, as suggested by some speculative theories. It also suggests regions where the laws of physics might differ. Considering these profound philosophical implications elevates the discussion beyond pure physics, encouraging contemplation of the vastness and strangeness of reality. The question of the universe's infinitude remains one of the most profound and active areas of research in cosmology. It is a testament to the power of scientific inquiry that such questions can even be posed and evidence gathered to approach an answer. The universe continues to hold its deepest secrets, inviting continuous exploration of its cosmic enigma.